So we're looking at these practice problems from yesterday. Hopefully everyone has the sheets. The first one I think you should have found relatively easy because it's just the same as the one I showed you yesterday, really, it's just a different angle, right? So you'll remember the couple words that we learned yesterday. Equilibrium and equilibrant. And more than once, a student has come to me during the test and said, Mr. Bennett, what is the equilibrant? I don't know what that word means. And I'll say, well, I talked to you about it in class. So, what is the equilibrant? It's the force that makes the system go into equilibrium. Okay? In other words, it's the force that makes the net force zero. And the equilibrant is always equal to the opposite of the result. That is correct, Chris. The opposite of the result. So you simply find the resultant and change the direction. Okay? Now, in this particular case here, it's already in equilibrium. Oh. Let's begin. The question is, what force does each rope exert? Now, what isn't on this diagram is the weight force. Yes, you do, yeah. Yeah, it's the practice problems. Now, from the previous example, it was 168 newtons, right? So the weight force is 168. I've got T1 and T2. T1 is equal to T2, right? And I've got T1V right there, T1V, the vertical component. So really what I want to write is T1V plus, now T2V is going to be exactly the same, so I'm going to say T1V plus T2V is 168. 2T1V, because there's two of them, because they're the same, is 168. So the vertical component is 84 newtons, right? Yeah. So I get 84 newtons of vertical force. I need to find the tension in the ropes. This is 42 degrees. Okay, so that's going to be opposite and hypotenuse. So it's going to be sine of 42 is my opposite, is my T1V, is my 84 divided by my tension. My tension force is just simply 84 divided by sine 42. Nothing too spectacular there. 126, we'll say 125.5. Remember that the greater the angle, the greater the tension in the ropes, exactly. Okay, let's move on to the second one here. An 8 Newton weight has one horizontal rope exerting a force of 6 newtons on it. What are the magnitude and direction of the resultant force on the weight, and what force and magnitude and direction is needed to put the weight into equilibrium? And that again is called the equilibrant. The equilibrant. Okay? So they're asking for the resultant of those two. The equilibrant is going to be that way, right? Okay. Now, do I need to use components here, do you think? No. How come? Because it's too simple, right? I mean, it's just a straightforward Pythagoras kind of thing. I've got an 8. I've got a 6. There's my resultant. So the resultant squared is going to be 8 squared plus 6 squared. And that's going to give me 10. What are the magnitude and direction of the resultant force on the weight? Now, we don't have any reference angles here, right? We don't have, this isn't necessarily south. This is actually, it's a weight. So I guess technically this is down, right? So this angle here would be, it would be the inverse tan of 6 over 8. (37 degrees). Now, how would you call that 37 degrees? Like, you have to give it a reference of some kind. It would probably say that it is right of vertical. Okay, it doesn't even indicate down though, really. Anytime there's no sort of north, south, or east or west, it kind of makes it hard to describe the direction. I guess you could say it's 37 degrees down and right of vertical. And the equilibrium is going to be the exact opposite, 10 newtons, but then it's going to be, if that's 37, then that would be 37 in there. Right? Kind of hard to describe. I would make sure on a test I would do a better job of giving you the direction stuff. So the steps are to find the equilibrium, find the resultant, flip the direction, right? That's really it. Okay. This one's a little trickier. Two ropes pull on a ring. One exerts a 62 Newton force at 30 degrees above horizontal. The other is a 62 Newton force at 60 degrees above the horizontal. So they're both 62 degrees, or 62 newtons, but one is 30, one is 60. What's the net force on the ring, and what is the equilibrium? So the net force is going to be somewhere in between, like that, which is going to make the equilibrium something like that, right? So, should we add these by components, do you think? We can't do it by Pythagoras, right? We really don't want to do scale drawing anymore. We're going to have to go components. Let's call this one F1. Let's call this one F2, and let's break them into components. Sounds suspiciously like the questions we saw on the first test, doesn't it? So, F1 is this one here. Let me redraw it. Let me go down. Okay, this is the 60. Call this one F1, F1V, F1H. Let's do the V's first. So F1V is going to be 62. The vertical is opposite, so that's going to be 62 sine 60. Or 53.7. I'm going to put my horizontal over here. F1H is going to be 62 cos 60. Really? 62 cos 60. Oh yeah, right. 31. Okay. Now those are both up and to the right, so they're both positive. Okay. Now let's draw the triangle for F2. It's very similar. The only difference being is that it's 30. F2V, F2H. They're going to be exactly the same, sine and cos. So F2V is going to be 62 sine 30, which is 31. And F2H is going to be 62 cos 30, which of course is the other value, 53.7. Both positive again because it's up and to the right. Am I going too fast? Good thing I was on pause there for the last 5 minutes. That was a good move on my part. Oh well. We got one more question, Justin? That's it? Really? Okay. Oh no, I got one more here. All right, so Matt has said that he would prefer to do this question on his own. Why don't you guys try this, okay? Give it a whirl, and then I'll do the answer in about 5 minutes, okay? Two forces exerted on an object, yeah? 36 Newton force acts at southwest, so that's exactly 45 degrees. 48 newtons acts at southeast. What are the magnitude and direction of the equilibrium? All right. Two forces are acting on an object. A 36 Newton force acts at southwest, and 48 newtons force acts at southeast. So I've got 36 this way, and I've got 48 that way. So the resultant is going to be kind of somewhere over there, right? No, it won't. It would be if the forces were equal, right? But they're not. So that's a good point. So I'm just going to draw them separately. I'm going to draw my 36 newtons like this. It's southwest. Let's just call this force 1. I'm going to call the other one force 2. So this one's going to be F1V. This one's going to be F1H. So F1V is, this time it's adjacent. So it's going to be 36 cos 45. We know it's 45 because it says exactly southwest. So 36 cos 45 is 25.5. And F1 horizontal is going to be 36 sine 45. 25.5. Big surprise. It's a 45-degree angle. The other one is southeast, which would be this way. Also 45 degrees, except this one is 48 newtons. So I've got, this one is F2V, this one is F2H. Vertical is opposite, so that's sine. So F1V is going to be 48 sine 45. 33.9. The other one, this should be a 2, shouldn't it? F2H is 48 cos 45. How do I do that? 33.9. Again.
That's so funny, Mr. Brown.
Now, do we have to worry about signs here?
Yeah.
We surely do, right? Okay, let's just make sure we got things right. So down and left, which means they are both negative. This one is right and down, so horizontal is positive, vertical is negative, right? So that makes my, now, should I do resultant and then equilibrium, or can I go straight to equilibrium? I think that seems hard, doesn't it? Like, I'd have to, let's just do it, yeah, I think we should just go resultant here. So let's go resultant V is going to be minus 25.5 minus 33.9. $59.4. That's negative. Resultant horizontal, it's going to be the same number because we're doing the same. Oh, hang on, it's not going to be the same number, is it? One's positive, one's negative. 33.9 minus 25.5, 8.4. And that's going to be a positive 8.4 to the right. Now, should I combine these and then go to my equilibrium? Because it doesn't actually ask for the result. Or can I, what do you guys think about doing this? What if I say, if the resultant vertical is that, then the equilibrium vertical is positive 59.4. Does that work? Just flip the direction? And the equilibrium horizontal would be minus 8.4. In other words, down, no, up and left. And now we combine those. So it's going to be 59.4 and a minus 8.4. Equilibrium squared is going to be 8.4 squared plus 59.4 squared. That's 60. Exactly 60 newtons. And of course we need an angle. Opposite over adjacent. 8.4 over 59.4. $8 degrees. Does that seem about right?
Yeah.
So now that's going to be, because we were dealt all that southeast and all that stuff, that's going to be really north. It's 8.04. North 8 west, isn't it? North 8 west. Is this any different than the vector addition that we did first unit? The only slight difference is you have to, the units maybe, or enforces, you're right, and the question is worded a little bit differently, and you have to flip your answer around to get the equilibrium, right? But basically the same concepts.